I am Dr. Vilas Chandra Roy, and it is my pleasure to serve as your session host. We now begin with our invited talks by two distinguished speakers in the field of inorganic and supramolecular chemistry. It's my honor to introduce our first invited speaker for this session, Dr. Arijit, the Associate Professor and Head of the Department of Chemistry at Tripura Memorial College, Agartala, India. Dr. Das is an accomplished researcher and educator working at the intersection of synthetic inorganic chemistry and innovations in chemical education. He has successfully completed two prestigious research projects funded by SARB, Government of India. He has guided 6 postgraduate interns, a project fellow, and a postdoctoral fellow under these projects. Dr. Das is known for his exceptional contributions to science pedagogy. He has developed 22 time-efficient, innovative teaching methodologies, invented 40 original chemical formulas, and proposed 6 advanced laboratory experiments in paper chromatography. His work also includes the launch of 2 AI-based educational tools in the United States, which have been indexed by some of the world's leading academic institutions, including MIT, Imperial College of London, University of Oxford, Harvard, Stanford, and City College of New York. He has secured 5 copyrights from the Government of India for his innovations and has published over 100 research articles, books, and book chapters in reputed national and international platforms. Dr. Das holds memberships in distinguished scientific bodies, including the Chemical Educations Divisions of the American Chemical Society since 2013, Indian Science Congress, India Academy of Forensic Sciences, and the Indian Chemical Society. He is also a recognized author on TEDx, U.S. Development of Education, Chemistry Library Tax, University of California, Davis, and Wiki Educator, OER, New Zealand. So today, Sir will deliver a talk on LP and NC discriminate hybridization with aromaticity reactivity patterns. Yes. Sir, I welcome you to come on the stage. Stage is yours, sir.
Thank you. আমি রবীন্দ্রনাথের একটা ছোট্ট লাইন দিয়ে শুরু করছি। এ মনিহা রামায় নাহি সাজে, এরে পড়তে গেলে লাগে, এরে ছিটতে গেলে লাগে. So I always place myself as a gardener for my flower-like students, and this will be my identity. Thanks. First of all, I want to give my cordial thanks to the Department of Chemistry, ICFAI University, mainly Dr. Shubhodip Bai, Amitabh Sharma, Tufan sir, and HOD of Department of Chemistry, ICFAI University. So I am working in the field of synthetic inorganic chemistry, along with innovation in chemical applications. And today I shall discuss the topics LP and NC, discriminate hybridization with aromaticity. Here LP stands for lone pair and NC stands for negative charge. So today we see how classification of lone pair and classification of negative charge discriminate or differentiate hybridization with aromaticity. So first of all, we know what is innovations. Innovation is simple thinking outside the book. That is, when you read the book, you must read the book, you must read the textbook, but when you think, you must think outside the book. It brings innovations. So simple thinking outside the book builds mnemonics and thus transports innovations, which makes the subject metabolic, time economic, and intriguing for students and educators both. And the simple thinking makes chemistry metabolic, intriguing, and time economic be the objective of innovational journey. What is mnemonics? In mnemonics, the first letter M is silent. So mnemonics is a learning device through which we can remember anything in our brain long time. And there is a internal relations between mnemonics with sustainability. How? In chemical education, sustainability means any object that lasts over time in human memory. So we can say mnemonics and sustainability both are correlated with the long-term journey. Now, what is hybridization? My discussion topic is mainly for UG and PG level students. So hybridization, we know hybridization is nothing but the mixing of two components. In case of chemistry, the chemistry is nothing but the orbitals. So hybridization is nothing but the mixing of orbitals in different ratio to get some newly hybridated orbital, that is mixed orbital. So this is the conventional formula for the prediction of the hybridization state. All the hybridization states should be predicted by using this formula. Here V means valence electron, M means monovalent atom, C cationic charge, and A for anionic charge. But it will be observed that when we predict hybridization state, there is a huge limitations of this conventional formula. You can't believe what types of limitations for this formula. Just you see. This is the conventional power of the hybridization state. When SP So, the conventional power of the hybridization state is like that. When 1s and 1p mix together in 1:1 ratio, then we get sp hybridization state. So, in this case, the power of the hybridization state is nothing but the summation of individual power. That is, you sum up power of s with sum up power of p. That is why the total power is, or the power will be 2, then the hybridization state will be sp. In the same way, for power of the hybridization state 3 for sp2. And for 4 for sp3. Now, in the innovative way, the power of the hybridization state. What is that? So here you see the conception regarding power of the hybridization state will be changed. Here I treat the power of P as the power of the hybridization state. So in case of sp hybridization state, the power will be 1, and in case of sp2, power will be 2. In case of sp3, power will be 3, like this. So this is the first formula. Power of the hybridization state equal to total number of sigma plus lone pair minus 1. That is, you first count the total number of sigma bond and lone pair of any central atom for which we should predict hybridization state. Then you subtract 1 from the total value of sigma and lone pair to get the hybridization state. So this is the first example for which we see the limitations between conventional and innovative formula. This is the cyclic ozone proposed by Linus Pauling. If you predict the power of the hybridization state as per conventional formula, then it will be observed that the value will be 3. It is wrong. Actually, for cyclic ozone, the power of the hybridization state and the hybridization state will be sp3 instead of sp2. So this is the one of the limitations. So how can you find out its hybridization state? Here you see oxygen having 2 lone pair. Each oxygen having 2 lone pair. So you should treat every single bond as sigma bond. In double bond, there is a 1 sigma 1 pi, and in triple bond, there is a 1 sigma 2 pi. So when you predict the hybridization state of oxygen, then there will be 2 single bond, that is 2 sigma bond, and there will be 2 lone pairs. So TSLP, that is total sigma plus lone pair, will be 4, and the power of the hybridization state will be 4 minus 1, 3. And the hybridization state will be sp3. So this is one of the drawbacks of conventional method solved by innovative ones. Second one, S8. S8 and tetrahedron P4. Okay. So when you predict the hybridization state of sulfur in S8 with conventional formula, it will be sp2. It is wrong. But when you use innovative formula, it will be sp3 and it is correct. So this is another drawback. So there is a huge number of drawbacks of conventional formula, and all these, you should find all these in this paper. This paper published from Indonesia in the Journal of Education and Learning in 2020. Predicting the hybridization state, a comparative study between conventional and innovative formula. You will see in the Google. Next, this is the second formula for predicting the hybridization state of carbon atom in different organic compounds. I am fortunate the Shopon sir is present here. And he is very eminent personality and my most favorite one. So here you see, when you predict the hybridization state of non-heterocyclic organic compound, then you use this formula. Here, LP should be replaced by LNC, localized negative charge. S stands for sigma. So you first find out total number of sigma bond and any localized negative charges there is not present or not. Then you sum up the total sigma with LNC and the subtract 1 from this to get the power of the hybridization state. This is the third one. And these formulas should be used while you predict hybridization state of any heteroatom in heterocyclic compounds. Here, LNC should be replaced by LLP. LLP stands for localized lone pair. Now, classification of lone pair is very interesting. How you classify lone pair from your necktie? Just দেখার সঙ্গে সঙ্গে বলতে পারবে which one is localized and which one is delocalized. How? When? So lone pair can be classified into 2 types, localized lone pair and delocalized lone pair. You see the figure. When lone pair containing atom, lone pair means number of electrons in the outermost orbit should not take part in bond formation. This is lone pair. Okay? So lone pair containing atom means heteroatom. So when lone pair containing atom directly attached with single bond from all sides, then these lone pairs should be treated as delocalized lone pairs. And when lone pair containing atom directly attached with single bond at one side and double bond with other side, then this lone pair treated as localized lone pair. In this way, student can easily classify which lone pair treated as localized and which one is delocalized. In case of thiazole, you see both lone pair looks like delocalized. But in delocalization, only one lone pair should participate. So other lone pair treated as localized. Okay? Same as for furan, same as for thiopene. Now, classification of negative charge. Here, in the same way, just like lone pair, negative charge treated as or classified as two types, localized and delocalized. In the delocalized, you see negative charge containing carbon atom directly attached with single bond. And in the localized, you see negative charge containing carbon atom attached double bond with one side and single bond with other side. So in this way, you can easily classify negative charge in lone pair as localized or delocalized. Now, using localized lone pair or localized negative charge, now we can predict the hybridization state we discussed earlier, and using delocalized negative charge and delocalized lone pair, predict aromaticity. How? So, Huckel's rules of aromaticity, devised by Huckel in 1931. The first point is that the molecules must be cyclic, planar, that is all carbon atoms having sp2 hybridization state. Third one conjugated, and fourth one 4n plus 2. Here, in the fourth one, here I replace this 4n plus 2 with a value. In the innovative way, you predict a value. If a value becomes even number, then it will be aromatic. If a value becomes odd number, then it will be anti-aromatic. So what is a value? You see, A equal to pi bond plus DLP plus 1. 1 is a constant terms. So total number of pi bond present in the cyclic system with delocalized lone pair with 1. If this A value become even number, then it will be aromatic. If this A value become odd number, then it will be anti-aromatic. And we know aromatic compound is more stable than anti-aromatic. So, classification of lone pair discriminate hybridization with aromaticity. Here you see LLP used in hybridization by using this formula, right? And DLP used to predict aromaticity by calculating a value. So in this way, by classification of lone pair, we can easily discriminate hybridization with aromaticity. So these are the examples. Huge number of examples is there. You see, pyrrole, furan, thiopene, quinoline, isoquinoline. Okay. Purine, thiazole, benzothiazole, azosine, oxyten. Okay. So in this example, there is a hybridization state of different heteroatoms. Okay. Now you see in thiazole, see in the example thiazole, you should predict the hybridization state of sulfur, because without prediction of hybridization state, you can't say it is planar. Because planarity means all atoms, it may be hetero or carbon, must have sp2 hybridization state. So for the prediction of planar, for identification of planarity, so prediction of hybridization state much more important. Okay. So now, in case of thiazole,
In case of thiazole, you see, you predict the hydration state of sulfur. So sulfur having two lone pair. One is in LLP mode and another is in DLP mode, right? And sulfur directly attached with two single bonds. So there is 2 sigma, right? So total number of sigma plus LLP in case of sulfur will be 3. So in case of sulfur, TS LLP will be 3 because all single bonds are sigma, right? So 3 minus 1. This will be the power of the hydrogen state, right? So it will be sp2. Same is for nitrogen. In case of nitrogen, here you see the lone pair of nitrogen is in LLP mode. So here 1 LLP and 2 sigma bond. Because in double bond there is 1 sigma 1 pi and in single bond there is a sigma. So there is a 2 sigma and 1 LLP. So 3 TSLP value. TSLP value will be 3. So power will be 3 minus 1 to sp2. Right? So in the same way, you can predict hydration state of heteroatom in case of other heterocyclic compounds. Here the list of heterocyclic compounds are given. Here you see in table 2 for the prediction of A value. How? In case of thiophene and quinoline, you see here. In case of thiophene, 1 lone pair is in DLP mode and another is in LLP mode. So there is only 2 pi bond plus DLP plus 1. So there is 2 pi bond plus 1 DLP plus 1. So the value will be 4 and it is even number and hence it will be aromatic. Now, in case of azosine, here you see, in case of azosine and azitine, here this lone pair treated as LLP and here DLP is 0. There is no DLP. Right? So in this case, number of pi bonds will be 4. So 4 plus 6 DLP 0. So we put here 0 plus 1. 1 is a constant term. So the total value will be 5. 5 be odd number. So if A value becomes odd number, then it will be anti-aromatic. So in this way, azosine is anti-aromatic. Next, negative charge. Classification of negative charge discriminate hybridization with aromaticity. In the same way, LNC, that is localized negative charge, used in this formula for the prediction of hybridization state of carbon atom or carbon bearing negative charge, and the delocalized negative charge treated or used for the prediction of A value for aromaticity determination. In the example you see here, cyclopropenyl anion, cyclopentadienyl anion, cycloheptatrienyl anion, phenyl carbanion, huge number of examples is there. So here, cycloheptatrienyl anion. In this example, you see these carbon bearing negative charge. We should predict hybridization state for this carbon bearing negative charge. These carbon bearing negative charge, these negative charge treated as LNC or DNC, localized or delocalized, because it is directly attached to single bond from all sides. So it is delocalized or localized? Delocalized. Very good. Delocalized. So it is delocalized. So here these carbon directly attached with single bond. So there is a 2 sigma and 1 delocalized negative charge. So total number of sigma plus sigma plus LNC will be only only 3, because there is a 1 hydrogen atom is there. Here there is a 1 hydrogen. So 3 single bond, 3 sigma. There is no LNC, only DNC. So value of LNC is 0. So the total number of sigma plus LNC will be 3 plus 0 equal to 3. So power will be PS LNC minus 1. That is 3 minus 1 equal to 2. And the hybridization state will be sp2. Right? So in this way, you can predict the hybridization state of non-heterocyclic organic compounds. Now, use of DNC for the prediction of A value for non-heterocyclic organic compounds. How? Here, you see, in case of cyclopentadienyl cation, we know cyclopentadiene is much more acidic over cycloheptatriene. Okay? Because the conjugate base, which is achieved or formed from cyclopentadiene, is aromatic in nature. Okay? And the conjugate base, which is to be formed from cycloheptatriene, okay, is anti-aromatic in nature. And we know aromatic is much more stable than anti-aromatic. So the conjugate base achieved from cyclopentadiene is much more stable than cycloheptatriene. As a result of it, the equilibrium shifted towards forward directions, which produces maximum number of protons and which increases the acidic character of cyclopentadiene over cycloheptatriene. So, in case of cyclopentadienyl cation, anion, here you see there is one DNC. So, pi bond will be 2, 2 plus 1 plus 1, 4, even number. So, it will be aromatic. So, very simple.
But the negative charge is delocalized, right? Cyclopentadiene anion.
Yeah. This negative charge.
Then you are writing localized negative charge 1. How it is done?
Localized?
No, localized negative charge 1.
No, this is GNC, delocalized.
Okay, writing is wrong then.
Yeah, writing right, yeah.
Okay.
Delocalized, GNC.
Okay.
Okay? Next. So, these are the examples. So, last one, cyclobutynyl dianions and cyclooctatrienyl dianions. Okay? So, these are the references. These are external links. Okay? And this is very important. Just you see. There is 38 formula in this SES index site. Here you see, yeah. Here you see, calculation of pi bond, sigma bond, single and double bonds in straight chain and cycloalkene systems. How? How you calculate? Very simple way. Any kinds of hydrocarbon units, any. Suppose you assume C200 and 800. C200 and 800. How you predict how many number of chemical bonds and which types of bonds are present there? In this formula, in formula 22, you see calculation of pi bonds and double bonds. Here, in this formula, you just put the value of X and Y. X is nothing but the number of carbon atom. Y with the number of Y is nothing but the number of hydrogen atoms. So what will be the number of X and Y, that is carbon and hydrogen? You just put in this formula to get the result. Okay. So this formula is used for calculation of pi bonds and double bonds, and second calculation of sigma bonds. In case of cyclic system, this formula should be used. So there is a huge number of formula, and this formula 20 is used for cycloalkyne or cycloalkyne systems. Okay, this one. Now, you see the use of formula to form AI-based tool by mineralogy.com. Next. These two educational tools, these are free access, launched in USA. First one launched in 2015 and second one launched in 2018. Hydrocarbon parser and diatomic bond order calculator. Yeah. Now, here you put the value of carbon and hydrogen, the number of carbon and hydrogen in the box. Suppose I put here C 300 and H 100. Okay. Now click on the play options. So this will be the result. It is invalid for open chain alkane. In case it exists as polycyclic alkane, in this case sigma bond will be 650. It exists as open chain alkene, cyclic alkene, and the total number of sigma, pi, single, double bond, all data are given here, along with degree of unsaturations. And these are indexing library where all these methodologies indexed. Thanks to all of you for hearing me. Any questions?
Thank you, sir, for such an engaging presentation. So now the platform is open for question answer. Anyone wants to ask question to sir, the platform is open. Even those who are in online, they can also directly answer this question. Anyone?
Sir, so can we predict non-aromaticity, homoaromaticity from the age groups?
Because when you predict the hydrogen state sp3, then it will be homoaromatic.
Or sp3?
It will be homoaromatic. Mono-homoaromatic for one sp3, bi-homoaromatic for two sp3. Because you already predicted power of the hydrogen state. So when the power of the hydrogen state will be sp3 along with sp2, then it will be homoaromatic.
For non-aromatic.
For non-aromaticity, either it is acyclic or it is non-conjugated. So if we violate first any one of first three, then it will be non-aromatic. Thank you.
Any more question? Thank you, sir. Now I request our dean, yes.